Good afternoon, everyone, and welcome to our webinar. Thank you for joining us this afternoon. My name is Jumana Tariq Abdurazik. I'm studying for a master's degree in petroleum engineering at University of Houston, and I will be your moderator this afternoon. Today, we're pleased to welcome Dr. Farouq Ali, a very special guest from University of Houston. Dr. Farouq Ali is a distinguished professor of petroleum engineering at University of Houston, a former professor of Pennsylvania State University, University of Alberta, and University of Calgary. He has worked on thermal recovery and enhanced oil recovery for nearly 60 years and on many projects worldwide. Dr. Farouq Ali has been honored for his research by the Society of Petroleum Engineers, the Canadian Institute of Mining and Metallurgy, and the Russian Academy for Sciences. He was awarded not one, but two honorary doctorates by two major universities in Russia. He is also a member of the U.S. National Academy of Engineering. And today he'll be sharing with us his expert opinion on natural gas engineering. If you haven't already, please make sure to check out our previous sessions on Pipetro YouTube channel and join our Facebook page, Arab Oil and Gas Academy, for the latest updates on our upcoming courses. Please feel free to send your questions in the chat box and we will answer as many questions as possible. With that, I ask you to give your full attention to Dr. Farouq Ali and help me in welcoming today's very honorable guest. Please welcome Dr. Farouq Ali. Hi, Dr. Farouq. Thanks for joining us today. We're so glad to have you on Pipetro.
Thank you, Joanna. It's a pleasure to be here, and it's good to see everybody, especially Dr. Al-Ghari and also you. And I hope you enjoy the lecture. A couple of words about myself. I'm originally from India. Agra is the place where our family lived. My father used to say for 1,000 years or something like that. And so to welcome you all, I'd like to say namaste, assalamu alaikum, and dobro požalovať. We will talk about natural gas. Natural gas engineering is one of my specialties. I've been teaching natural gas engineering for a long time. This lecture was especially designed for this to fit the time frame and also to fit the needs of the what we are doing here. So I'm very happy to have you all, and you can send the questions and I'll try to answer them. The first thing is this: I always like to show the oil price and gas price. So you can see here the oil price is going up on the right side, and it's now almost $57. And on the left side, you see the gas price is also sort of going up, is down slightly. Those numbers are extremely important to us, especially to me. I've been watching those prices for more than 60 years now. Just to give you an idea, in 1960, when I started my work at Penn State University, oil price was $1.10 for West Texas, $1.10 a barrel. And would you believe Kuwait crude? Kuwait, is a country in the Middle East. I'm sure you know that. Kuwait crude at that time in 1960 was 59 cents a barrel. Can you imagine that? Anyway, so gas is a very special kind of fuel. It's the fuel of choice right now. We'll see a little bit of that. And you see, I put a lot of unnecessary information on the title slide. I always do that. Okay, so the first thing I'd like to tell you about the different things we'll discuss. A little bit about natural gas definition, what it is, then about the reserves and calculation reserve. That's the main topic. We'll do a couple of examples also. And then very short topics are natural gas in the world and future of natural gas. That's the agenda, more or less. Dr. Al-Ghari asked me to essentially concentrate on natural gas reserves in this particular lecture. I gave him almost a dozen different choices, but that's also a subject of great interest to me. First of all, where does natural gas occur? This diagram is taken from one of the listings on the internet, so you may have seen it. But all I want to say is it's a rather nice diagram, because what you see here are natural gas accumulations. The ordinary natural gas is this here, where you have a gas reserves under an anticline. I'm sure you all know different types of traps. And then you have also another situation here on the right side, where you have conventional natural gas above an oil zone, whereas the other one was gas by itself. So when you have an oil zone, there's a water zone too, which is not shown here. So those are the conventional in the sense of ordinary gas that you talk about. Now, other than that, we have tight gas. You see tight gas here. Tight gas has been around for a long time. Essentially, all it means is that we have a reservoir where the permeability is of the order of a fraction of a millidarcy, maybe 0.1 millidarcy, maybe 0.2, something of that order. And then you hear a lot about shale gas, shale oil. That shale oil is this last one here. That black thing there is shale. Shale is a general word for clay. There are many kinds of shales or clays. And shale is also the source rock. You understand, I'm sure, source rock, where the oil was formed. Source rock is a very important item in any oil field development. If you find an oil field, such as you see here on the right side, you like to know where is the source rock, because that will give us an understanding of the field and also what might have happened and why there are changes in the oil or over the extent of the field and so forth. Now, the source rock and what we call oil shale now, shale oil and shale gas, is extremely tight. The permeability of shale, where the gas occurs, we talk about gas really, the oil also, you're talking about a permeability in the range of 10 to the minus 9 darcies. Very, very small permeability. And you know, the biggest shale oil reservoir was discovered, the biggest reservoir. Now, you know, we talk about the biggest reservoir in the world, Eagleford. The biggest reservoir in the world is known to be, as you well know, is the Gawar field. The Gawar field in Saudi Arabia, I've worked on many occasions on that, by the way. That's the largest reservoir, almost 250 miles long and 50 to 60 miles wide. Gigantic reservoir, 400 foot thick. You have to fly over it, you know, it's so big. It's too long to drive. But in any case, now the biggest reservoir, if you look at all kinds of oil and gas, is Eagleford. Eagleford has gas, it has oil, it has even viscous oil, heavy oil. Not that much, but Eagleford is the largest reservoir. The four largest reservoirs in North America are, not counting Eagleford, this East Texas, Yates, Pembina, and this is Pembina is in Canada, and one of the other reservoirs, Spindletop, I forgot that for a second. Those are the largest reservoirs in North America, but now Eagleford, how much oil is in Eagleford, nobody knows. Okay, so the main thing I'm trying to say is that gas occurs in several situations. Many a time you talk about only the conventional gas, where gas reservoir is by itself. And remember, there's water underneath. Wherever there is hydrocarbon, there is water also. You hear about dry wells, you drill a well and it's dry. Trust me, no wells are dry. They are full of water if there's no oil. Okay, so let's go further. The properties of oil and gas. This table here is from the famous Kraft and Hawkins book. I like the original Kraft and Hawkins, and this is taken from there. And they show the composition of black oil, volatile oil, and gas condensate. I won't talk about those. And also dry gas. This is our main topic here. And we have the composition here, C1, C2. And what you see here, there is a preponderance of methane, 95.85% by volume. And then there is also C2, ethane, and then there is propane and smaller amounts of other components, but very little of the C7 pluses. That is dry gas, and the molecular weight, if you really want it, is 100. Although if you talk about methane, you know it is only 16. And if you talk about GOR, which is really not very meaningful for a dry gas reservoir, but you can see it's a very high number. The API gravity, well, GOR is 105. I'm mixing up things a little bit. The molecular weight was 157, GOR is 105. The tank gravity in API, again, these are not particularly useful numbers, but you can see that dry gas consists of these. And in a general sense, when they talk about gas, then you see another composition here on the right side. But this is our main interest in this lecture. A little bit more about gas, because what is gas? The produced gas is often a two-phase mixture, as you just saw. Separator gas and liquid measured at the surface. You know, gas processing, you have to refrigerate to knock out all those liquids. And this gas gives you, as a result, natural gas liquids, which are extremely valuable products, principally propane and butane. Where does it come from? Natural gas. There's a gigantic market for propane in the US and Canada. In Canada, especially because, you know, they have huge amounts of heavy oil and they need propane, principally propane as a diluent for various reasons. And then finally, we have non-associated gas, associated gas, and also solution gas. So these are different categories of gas, and we won't be too concerned about which category is which. Basically, we are talking about gas with as I just showed you, with a large amount of methane in it. That's what we're talking about. But there's an awful lot of associated gas produced in countries like Saudi Arabia. If you are producing oil, you're producing gas. There are no two ways about it. So what do you do with the gas? Flare it. That's the usual way they do it. In the world, I'll show you that somewhere later in the slides, 14.5 billion cubic feet of gas are flared every day. 14.5 billion cubic feet are worth $50 million. $50 million at a price of $3 per MCF. MCF is 1,000 cubic feet, or 1 million BTUs, or 1 gigajoule. They are all about the same. So associated gas is now being used in Saudi Arabia, for example, and other countries. Still today, we are flaring 14.5 billion cubic feet of gas, SCF. And you know, there's not that people don't know that they're wasting energy. It's very hard to utilize, but I won't go into that. I could talk about that for a long time. I visited the flares in Saudi Arabia when they were burning 3 billion cubic feet a day, and they were amazing thing to see. You cannot go even within a mile of those flares because they're so hot, and they are refrigerated. Would you believe that? The flares are not just cooled, refrigerated. Otherwise, the steel will melt in no time. Now, I'll take a minute to tell you one thing here, which is quite useful maybe. You know the Z factor or the Z factor for a single component gas? The gas deviation factor, for example, there are different names, compressibility factor. And you know, That comes in all calculations of gas. How do you calculate the Z factor? Well, you calculate the reduced pressure PR and reduced temperature TR, which is simply PR is P over PC. PC is critical pressure, and TR is equal to T over TC. TC is the critical temperature, and they are both in degrees R or degrees K if you're working in SI units. I know in a lot of countries, including Canada, where I was for a long time, we use the SI units. Okay, so you can, of course, from your uh, petroleum engineering courses that you calculate the reduced pressure, reduced temperature, and then you go to the standing catch chart. Standing catch chart is very famous. Uh, I knew standing very well, and I know catch quite a bit too. In fact, you may be surprised, but I met just about everybody who is important in petroleum engineering. You give me any name, and most likely I have met him one way or other. Sometime only to say hello. That was the case with William Hurst, the fellow who did the Hurst Van-Evertingen equation. Okay, so you can go to a standing catch chart and find the Z factor, which is fine, but there are equations too which are useful. And the reason you need the Z factor is that you need to calculate BG. Actually, BG, I'll say a few words about that in a minute. BG is a very clever way to convert the surface volume, which is this, to the reservoir volume, which is this. So petroleum engineering came up with this clever way. Well, there are other ways of doing it in chemical engineering, and they are much more complicated. But petroleum engineering came up with this idea that you take the surface volume, which is the standard volume, and multiply it by BG, and you have the reservoir volume. Or you take the reservoir volume and divide by BG, and you have the standard volume. Very clever. I mean, if you really think about it, then you appreciate after you actually see the methods they used in chemical engineering. So BG is the gas formation volume factor. That's what we call it. And you can derive the equation very simply. You want the volume, reservoir volume of 1 SCF. So this part of the PV over ZNRT is at standard conditions, and this part is reservoir conditions. Okay, so for 1 SCF, we'll now write BG, cubic feet in the reservoir. And then you solve for BG and come up with this equation here. I'll look at this one. I've written in other forms, no time to go into those. But this is the BG equation. That is what we live by. And this equation, as you can see, involves the Z factor, the temperature T, reservoir temperature in degrees R or degree K, and the pressure, reservoir pressure P. Simple equation, but the Z factor throws a monkey wrench into it because Z factor can be calculated different ways, and you can do it graphically, or you can do it on a calculator. Now, I should tell you this too, which is very interesting and useful, that this BG is not applicable to shale gas, okay? If you have shale gas coming from a shale where the pore size of shale is, would you believe, 1/100th of a human hair. A human hair is 200 microns. So the shale pores are that small. And at that size, the molecule size is about similar. So BG, as calculated here, will not be applicable to shale reservoirs. You have to use a slightly different equation. Well, it's quite different, but we won't go into that. So now the Z factor calculation is, this is not my subject, but this is endemic to all what we are discussing. So Z factor, I don't know whether you ever ran into Popeye's equation. Popeye, to be sure, it's not Popeye, okay? It's Popeye. He was a Hungarian scientist, a close friend of mine, and he came with this equation. And it's surprisingly good. It's not very accurate at the end points, but it's extremely useful and good because, as you can see, it involves only PR and TR. So we often use it on calculators. However, if you want really accurate equation, then there is this Drenchak-Abu-Qasim equation. Can you read it? In my screen, doesn't show very well, but Drenchak-Abu-Qasim. Abu Qasim is a professor, one of my former students, in fact. He is a professor at the Al Ain University in UAE. He came up with this equation. This was his MSc thesis. Can you believe that? For the MSc thesis, he came up with this equation. And this is the most accurate equation. There's a lot of publication papers on it, where they compare it with other equations. So I showed you the Z factor equations because they're very useful, okay? And now we'll talk about gas reserves. So we want to know how to calculate gas reserves. What is the word reserve? Reserves. When we say reserves of oil or gas or anything else, metals too, reserves means the resource means what is in the ground, and multiplied by the recovery factor. So that's the definition of reserves. In other words, if we have, let's say, 1 trillion cubic feet of gas in the reservoir, and we have a fairly good idea that this is the resource, then the question is, how much of that can we recover? If we can recover 85%, we'll be lucky, okay? Now, if you're talking about oil, then the recovery factor will be more like 30% if you're lucky, or maybe less. Now, sometimes it can be higher too, but that's rare. Okay, so to calculate the reserves, you can see it's a rather important calculation because reserves are calculated based upon the current technology for recovery and also the current economics, okay? I'm sure you well know that. If the gas price is high, we can recover more gas. Right now in the US, we saw on the first slide, the gas price is only about $2.50 in that range per MCF, MSCF. Now the gas price in Europe is far higher than that, twice. If you go to Japan, it's much higher than that, maybe $15 per MCF, because they have to rely on liquefied petroleum gas and re-evaporate it. Okay, so we have a number of ways of calculating gas reserves. The first one is volumetric and analogy. Second one is the material balance equation. Third one is decline curve analysis, and the fourth one is reservoir simulation. We don't have time for reservoir simulation, but I'll be happy to answer questions on that. We have done an awful lot of work. Several of my former students wrote their MSc thesis and PhD thesis on gas reservoir simulation under various conditions. So we'll only talk about the first one, volumetric. Second one, a little bit on material balance equation, and a little on decline curve analysis. Okay, volumetric and analogy, we'll take that first. Analogy is not a particularly good way of doing it. Analogy simply means that, let's say you have a reservoir here, and it happens that far away from there, there's another same reservoir formation. So you ask your geologist that, is this geologically similar or not? And they will say, yeah, it is geologically similar. So looking at the properties of your reservoir, which is this, and this reservoir away, you can tell that, okay, maybe the recovery factor will be such and such, and your geologists tell you that there's so many trillion cubic feet of gas in it, and you can come up with some sort of reserve picture. Not a very good way of doing it. I said your reservoir, right? Of course, if you find gas in any country, the gas will belong to the government. There's only one country where it belongs to you 100%, and that is USA. No other country like USA. In United States, if you drill a well all the way to the center of the earth, then everything that you find is yours, 100%. Okay, quite amazing, right? So that's why 95% of all wells ever drilled in the world have been drilled where? In USA. You drill a well and you run your own oil company. I tell all my students to run their own oil and gas companies. And would you believe that more than 20 of my students right now are running their own oil and gas companies, most in USA. If you in Canada, you don't own the oil or gas, but you can still get 70, 80% of the income. Not too bad. Okay, so analogy is not a good way of doing it. Volumetric is the way to do it. Volumetric essentially means that you're saying that we have a constant volume reservoir. You see volumetric all the time. It enters into material balance equation also. So volumetric reservoirs essentially means that geologically they are a constant volume. So sometimes we'll see this diagram in a minute. We draw this funny diagram is the classic diagram of a reservoir they show for volumetric reservoirs. So we are saying that here down below in the ground, there is a reservoir which is shaped like that, and its volume is constant. So here is your reservoir. It is at the initial pressure, and this is at some later pressure. Oh, it can be higher too if you pressurize it, okay, but we won't talk about that. So at both pressures, the volume of the rock, reservoirs are pore spaces. So the volume of the rock at both stages is the same, and we'll see that a little bit. But before we do that, in general, if you're talking about gas in place, this is gas in place. Well, it's written up there. I don't have to write it again. G is the symbol that we use in petroleum engineering for gas in place. You remember we use N for the oil in place, standard volume of oil in place, standard volume of gas in place, and we use the W, capital W, as the standard volume of water in place. Okay. So what is the gas in place? Not reserves. Remember, this is the resource. And that's very simple. Area of the reservoir. If this is your reservoir, then you take the area here and you multiply it by some average thickness here. So that gives you the volume. And then phi, everybody knows phi is the standard symbol for porosity. Porosity can be a fraction or it can be a percentage. Be careful which one you're using. And 1 minus SW. As I told you that whether you have oil or gas, there is always water present in some ways. Most of the time, it's interstitial water, and the water it's assumed that the reservoir is water weight. But it can be in other forms too. So we have to subtract that, okay? So in the pore space, if I draw the pore space, SW is water. So that's why we have 1 minus SW. So multiplied by the bulk volume AH, which I just showed you, this is the area A and thickness is H. And porosity phi, which is a fraction, and multiplied by 1 minus SW, which is the interstitial. Interstitial means which is present from the beginning. So that gives you the gas saturation, assuming that there's no liquid. Sometimes there may be a small amount of liquid, but we will assume there's no liquid, only water, so 1 minus SW. So that gives you the volume of gas in the reservoir. And you must express it as the surface condition because all our prices, everything in SCF. SCF is the volume at 14.7 psi and 60 degrees Fahrenheit, standard condition, a little bit different from NTP, okay? So what we do is this, we divide the G by BGI. Remember my rule? When I'm teaching classes, I repeat it so many times that the students get sick hearing it. So reservoir volume by B divided by BG is the standard volume. Okay. So this is the reservoir volume and you divide by BGI. I simply means that the initial pressure which I showed you here. And that gives you the volume of the gas in the reservoir in SCF, standard cubic feet, or standard cubic meter if you are using SI units. A standard cubic meter is a big volume. So one is, I mean, it just as a digression, if you use standard cubic meter, one is standard cubic meter is 35.3 SCF, large unit, okay. Okay, so this is the formula here. And here the area A is in square feet. Now in petroleum engineering, we use acres. And then also sometimes we talk about barrels. So here, look at the one down below here. Here we have the same equation as the first equation, but I have multiplied by 43,560. This is the number of square feet in an acre. A is in that case an acre, not in square feet as before, and so forth. And again, we divide BGI. So the first equation and the last equation is the same. The middle equation, you can ignore it for now because in this case, we are calculating the gas volume in stock tank barrels. Sometimes we have to do that when we are doing material balance calculation. So don't worry about it too much. So what we'll do now, we'll do a simple problem here, very simple problem. The picture is not very easy to, at least I have difficulty seeing. Let me see if I can move this thing here. Yeah, I can move it down below. Okay, so we were here. So what you do is this. It's a volumetric reservoir. It says here, calculate the initial gas in place in a volumetric reservoir. So we want G, that's what we are looking for. Okay, so draw that little picture which I had previously. We have gas in the pore space, G. So if you multiply, now G is, remember, is an SCF. And remember my rule again, multiply the standard volume by BG and you have the reservoir volume. So what you see in this square is the pore space occupied by gas when you multiply BGI in cubic feet of reservoir. So that is the first stage. In the second stage, we have produced some gas, GP again in SCF at a BG factor. The formation factor is now, pressures are different, remember from the previous diagram. So how much gas is left? G minus GP. And because we are saying that there is a volumetric reservoir, so G minus GP, and if you multiply it by the current pressure P, we calculate the PG using that equation I showed you, and multiply G minus GP by PG, you get the same volume, reservoir volume. So you can write your equation, which I didn't write here, but I'll write here. This is the rock volume occupied by gas at initial conditions. And this is the rock volume occupied by gas at the final conditions and multiplied by BG. The two must be equal. Very, very clever way of doing it. This material balance idea was one of the great advances. Does anyone know who came up with this material balance idea? You can type your answer if you want, but it was Schildius. It's written like this, but they pronounce it Schildius. Schildius, I met him only once briefly. You know, I was still a student at the time and saw him at one of the SP meeting when he was getting an award. Number of people I met like this, but I got near them to tell them my name. But it doesn't matter. But Schildius came with this equation first. Then later on, other people, especially Tracy and others, they modified it. So it was a very, very clever idea. So this equation that I just wrote, if you rearrange it, it becomes this one here. So all you need to do, we need to have G, we are calculating G, which is given by rearranging this by this equation. Plug in the numbers here. This is the produced gas, and this is the BG at the final pressure. And this is the BG at the final pressure minus BG at the initial pressure. And you came up with this 11.4 10 to the 9 cubic feet. So it's a very simple calculation and extremely useful calculation, by the way. But the thing to see here is this. Look at this. BG, we are taking two BGs which don't differ a whole lot. Look at these two BGs. So you can see that if you have just one second place decimal error, let's say 0.47 is 0.48, and your gas in place becomes half of what you had previously. So these values have to be determined with great care in a lab. And here is a little something which I can tell you from my experience. I didn't tell you that I have worked on more than 400 field projects. People won't believe that, but I can give you a list of all the fields I have worked on all over the world. So I have some experience of these kind of things. So what I was going to say is this, that if you have an oil or gas sample and you have the BG determined in a lab, then have it done in 2 labs at least, okay? Because there may be errors, and a small error can throw you off. So, you know, when you do all this, you can calculate BG, but you also have it done in the lab. Remember the liquids and all that? Okay, so that was a simple example to show you the calculation of reserves. In a practical sense, you have to calculate the bulk volume. And the bulk volume, the reservoirs are not nice and clean looking like a rectangle. They are something like this. So here's a gas reservoir, and this is the base of the reservoir maybe. I haven't drawn it very well, but you can see that you have a very uneven reservoir, and you have to find the volume. So what you do is, you know, from your high school, that you divide into strips. Each strip has an area A. Each strip has area A, A1, A2, A3. I don't have to go into great details. And then you want to see, you see that, well, maybe just approximated by frustum of a cone, which is this. Circle here, circle in the bottom, not good enough, okay? But you may want to do it. Maybe you're in a desert island and you're in a hurry and you do it like that. But make sure to do it accurately, which is the equation down below. I have an example here, which I took from Kraft and Hawkins, actually. You can look it up in the Kraft and Hawkins book, but it's a simple example. Same diagram that I had before, but I have divided into these layers here, as you see here, 6 layers. And for each layer, I have the area of the bottom of that layer, A1, A2, A3, starting from A0, which is the top. Given that, if we use the formula in the bottom of the page here, you can calculate the bulk volume. So I won't go through that, but it's a very straightforward calculation. Again, calculate the area of each of those layers, and you have the interval. We chose them 5 feet apart here. The top one we took at only 2 feet, or 4 feet rather, 4 feet. So it's a simple calculation. So once you have the bulk volume, once again, you have this number AH as one number. This is the bulk volume AH. And you can once again get the gas reserves. Volumetric, that's why I call them volumetric. One other thing that bothers us in these calculations, which is from my experience is very messy, and that is the average pressure. What pressure will you use, and do you have that pressure? You see, you discover a reservoir, and all you have is one pressure. Maybe you drill another well, and you may have another pressure. You know, I worked on this in the field a bit, and it's a really tricky matter that you discover a reservoir here, let's say gas reservoir, and they will ask you, where shall we drill the second well? Here or where? If you made the wrong decision, it's a $10 million decision. Oh, much more if it's offshore. So you have to be very careful. But initially, all we have is one pressure, so we can do very much. But at a later time, maybe we have several wells. Which is shown here. You know, you have A, B, C, D, every one of those quadrants. What I've shown here are isopex here. Constant, these are constant thickness line, thickness line. And these lines here are constant pressure lines. So you'll need to have an awful lot of data to draw those lines. But once you have those lines, you can calculate the pressures in each of these average pressures by using the corner values. And then you can calculate the average pressure on the basis of the number of wells, or on the basis of the area, or on the basis of area and thickness, both. So you'll have to have thickness contours. Well, we have also isopex here, so you can use those isopex also. So we can do it either way, and here is an example. The answers, if you have a lot of data, that is, which we don't have initially. Initially, it's a very tough job. You see, you discover a reservoir. Well, in Texas, do you know how many oil production companies are in Texas? How many in the world? You say ExxonMobil and Shell and all that. In Texas alone, there are 6,000, fully 6,000 oil producing companies. Maybe 20 of those belong to my students. I know one of them is in Oklahoma. He is doing very well also. So 6,000 oil companies in Texas. Anyway, so to come back to what I'm talking about, I took an example here, and if you have a lot of data, you can do the calculation on the basis of the number of wells, and you get this value. This value. If you do it on the basis of area, you get this value. And if you do it on the basis of area times thickness, which is the most accurate, you get this value. But you have to have an awful lot of data for that. Initially, you are lucky to have just one value, and you make a estimate of the gas in place on the basis of just one value. You see, the problem is this, that if you have your own reservoir, and my students have gone through that, they never discovered a new reservoir. By the way, that's a very expensive business, but you can buy a used reservoir for sometimes for $1. Would you believe that? And then you go to the bank and say that I want to borrow $10 million to develop this reservoir. So they will say, how much recoverable gas you have? And then, you know, you're lost and you're wondering what to do. Well, no, it's not like that, but it takes a lot of work. But once again, it's extremely impressive that we have 6,000 oil producers in Texas. And here to surprise you even more, plus another 6,000 supporting companies. Would you believe that? Incredible. But that's how America is, land of opportunity. And you can do it anywhere in the whole of America, except one state. Anybody knows? Alaska. In Alaska, you cannot own your own oil field. On the other hand, the government mails a check to every man, woman, boy, girl, cat, and dog every year. Maybe you are getting a check for $3,000, maybe $1,500, depending on the oil income. So the government recognized the fact that you cannot own your own oil field. However, you have a share in the oil and they send you a check. How is that? I know one of my friends there, he had several children, wife and himself, and he used to get 1 year when they were sending only $1,000, $1,200, he got $9,600. So pretty good. Alaska, yeah, I've done a lot of work in Alaska, lovely place. Make sure that you visit Alaska. Do you know, I hope I don't offend anybody, but March, which is coming up, I celebrate March especially because in March 1867, Russia sold Alaska to America for $7 million. That's all. Alaska was sold to America for $7 million, and I show people even a picture of the check. But there were special circumstances. But if you go to Alaska, you'll see some signs of that. People will remind you of that. Okay, so we talked about how to get the pressure and gas in place based upon that. What are the important variables in this calculation? We already looked at one, but how about porosity? That's a real big killer variable. Because how do you get porosity? You say from cores? Well, maybe, but where do you take the core? All over the reservoir? Maybe you have just one core. You need also the cornet water saturation. Both of those initially at least will come only from logs. Well log analysis is a very important part of petroleum engineering. I used to teach a course for well log analysis. I taught it for 25 years. And I gave them a lot of examples from my own experience. So well logs will give you initially a porosity value and a cornet water saturation. Later on, you'll have cores, you'll have more logs and more wells, and you'll say, oh, well, we over-calculated the porosity. Actually, the gas reserves are lower than what we declared. Similarly, the cornet water saturation, very hard to get. Logs are again the source for that. And pressure, of course. So you can see that a little error in all these variables will cause a big error, maybe in your calculation. And that is still another important variable. We haven't seen it yet, SGR. If there's a water drive, then what will happen is that the water will push some of the gas. A lot of gas will stay trapped. What is that? And again, a big unknown. So you can see that we have all kinds of obstacles in our way here. Okay, now let's go to the material balance calculation. Actually, what I showed you was the material balance equation, but in a very simplified form, where I showed you those funny-looking reservoirs. But I will just do a little bit on it here. Material balance equation is same thing, same. You draw those domes here, and you say that initially there was gas G, later on there's gas G minus GP, because we have produced GP. That's what we did before, and we have the initial pressure and we have some other pressure. But this time we have something new. We are saying that from somewhere some water has come into the reservoir. And this is WE. And we have also produced some water at the surface. And this is WP, like GP and NP. So again, you write a volumetric balance. You know, what I had before was this. Now I have added WE, which is because it entered, and I have subtracted BWWP because we have produced it, and BW is the same kind of thing. The magic number to change the surface volume into reservoir volume and reservoir volume to the surface volume. And maybe I'm already repeating it for the sixth time. This is a very clever way. Who came up with that? We must give credit to Schildius. Schildius was an amazing person, but he doesn't get much mention. Okay, so quite often what happens is that we have the value of G from geology. Geologists are very, very valuable people. Okay? Always respect the geologists because they determine what is G or what is N in the case of oil. And they will keep repeating those numbers and until you go crazy, doing simulations. But that's the nature of petroleum business. Okay, so I'm writing again the same material balance which I did before, but this time I'm saying that WE is entering and WP is produced. That's it. That's the material balance approach. And now I can make it much more elaborate. I can include rock compressibility. I can include, gas compressibility is already there in the BG, but I can include also water compressibility here. So we can do things like that. This is, and also, this is the important thing which I was going to say, which I didn't, that when water invades the reservoir, this red area, I have different colors, but it will take time. So within this water invaded zone, some gas is trapped, SGR. How much is that? And here's a table taken from Kraft and Hawkins' book. No, it's Kraft. Here we have SGR, residual gas saturation to water for different situations, different sands. You have, for example, unconsolidated sand. So look at this. I can't see this, but in one case, torpedo sand, 10 sleep and canyon reef in the bottom, which is the limestone, the gas which is trapped by water is that much, 50%, huge amount, okay? So you need to have that number somehow, okay? And if you really want to do it properly, you should have a core and send it to a lab. Those things are not cheap, okay? But it's well worth the money. Okay, so material balance, and again, this is the same equation that we had before. But what I'm doing, which you cannot see very well, is that I'm taking that equation on the top here. I skipped a lot of algebra here. And then I've rearranged it. When I rearrange and adjust the variables, I come up with this equation. So there's no difference between this equation and the previous one. The only thing I have done is that I have spelled out the BG, okay? So as a result, I end up with P and Z and PI and ZI. PI and ZI is fine because that's constant. P and Z are not. And on the other side, you have cumulative gas produced GP and the gas in place G, which we are hoping that our geologist friends gave us a good number for that. So the final equation becomes a really neat equation. GP, cumulative gas produced, versus P over Z is a linear function. It's an equation of a straight line. And people then said that, let me go to this graph first. Why don't we plot P over Z on this axis and GP on this axis, and you should get a straight line if everything is okay, no water coming in, okay? If everything is just volumetric, in other words, you'll get that straight line. And then you say that, okay, just extend it. And when it cuts the axis, which is zero pressure, we are saying that this is zero pressure, and this pressure may be 5,000, but is divided by the Z factor of, at 5,000, okay? It will be similar value to, so it will be probably 6,000 or something. But the main thing is this, that when we extend this line, we have G, the gas in place. Clever way to find the gas in place. Now, things get a little bit messier when you have water coming in also, because in that case, we'll have water invading. And this equation won't strictly hold, because then in that case, we'll have to have WE, and we don't have a simple way to do that. So what we do is this, we plot the data anyway, P over Z versus GP. However, this time we get this, maybe this line, maybe we get this line, maybe this curve. So what does it mean? All it means is that there is water drive and you go back and do your homework, because we neglected it, hoping that we'll get a nice straight line, and we didn't get it. So we go back and we find, oh, we have to sometimes assume a WE to see where the curve that we just got is, let's say this one, this is what we got. What WE will give you that? So you can see the problem becomes much, much harder. Now, if you have a perfect water drive, in other words, the water is coming in and maintaining the pressure, then you will get this straight line. Now, what about this other line? I said geopressured. What does that mean? Well, if you see the Gulf of Mexico, if I try to draw the map here, this is Louisiana, and this is Texas, okay? And this is the Gulf, we call it Gulf of Mexico. Or if I say Gulf, that's what I mean. So offshore Gulf in this area, we have thousands of wells, by the way, thousands of wells. The Macondo well, which blew out of control, is somewhere here. But we have thousands of wells. That was just a bad luck situation. So what I'm saying is this, that in this area, there are many salt domes. You've done from your geology, you know what salt dome is. So salt domes pressurize the shale so that they become abnormally pressured, not the hydrostatic gradient, but much more than that. If you are interested in that, there's a book by Fertel, Fertl, good friend of mine from Hungary also. And there's a book by Fertel and Chillingar, which is also on abnormal pressure. So in other words, if you have a situation like that, you get a curve like that. How do you deal with that? That's a big, big question. And you have to do a geomechanical simulation. So it can be done, but it's a little bit more. Now, one of the questions I asked the students, I didn't know there was a quiz in this exam, otherwise I would have left it for the quiz. Why aren't the abandoned gas reservoirs? What does abandoned mean? Here's a gas reservoir, and let's say there were 20 trillion cubic feet, which is a lot of gas, by the way. This is the gas in place, and we recovered 85%. Then 15% of that, 15% of 20 is 3 trillion cubic feet. I mean, that's worth billions of dollars. How do we get out of the reservoir? Well, you cannot get it out of the reservoir. In theory, you can water flood it like a oil reservoir, but it won't make any money. So I've given an example here. 1 barrel of water displaces, let's say, 1 barrel, or in other words, 5.615 cubic feet of gas at this particular pressure. This is the abandonment pressure. Can you believe that? Sadly, we have to leave a lot of gas behind because we cannot pump it out. You don't use pumps to flow the gas out. You have to make it flow. So let's say we inject 1 barrel of water and we produce this many cubic feet of gas. And this volume will be in SCF using our BG magic factor, 155 cubic feet. How much is it worth? 40 cents. Now, if you have 1 barrel of water and displacing oil, then maybe you'll displace zero point 0.5 barrels of oil, which may be worth $35 or at least $25. So you can see that you cannot make any money with 40 cents. That's why the abandoned gas reservoirs are not further developed by water flooding. However, they are quite useful for storing gas. If you want to store gas, like at one time in Pennsylvania when I was there, gas was rather scarce. You know, we used to pump it or pipeline it from Midwest. Now there's a huge amount of gas in Pennsylvania from the Marcellus Shale. Shale is everywhere in the US and also in the world. So Marcellus Shale is producing all that gas. But before that, we had many depleted reservoirs like this one, which already have a lot of gas left over. And this gas then served as what we call cushion gas. In other words, next time around, when you produce that reservoir, you won't have to worry about leaving any gas because it was already there. Okay. Okay. The next thing, last item, more or less, we did a little bit on volumetric, a little bit on material balance equation. And you probably noticed that I cleverly left out a couple of slides because we don't have enough time and they don't have anything terribly important anyway. So now we are on decline curve analysis. Decline curve analysis is one of my favorite subjects because it's so simple. And in spite of the fact that we have all these high power simulators, we still do decline curve analysis. So what is decline curve analysis? Decline curve analysis means this, that you have, let's say, oil field and it's producing gas at a rate Q with time. Okay. So you have the field history and you plot a curve like that. You're plotting a curve like that. And you want to know what is the production at this time. So what will you do if you don't know anything at all about petroleum engineering? Then you say that, well, just take a pencil and maybe a flexi curve and extend it. That's it. That's decline curve analysis. You hardly need any degree in petroleum engineering, right? So what is so special about what I'm talking about here in decline curve analysis? Well, making that extension is rather tricky, right? Because you have to have a good flexi curve. So people said that, well, come up with some mathematical way to change that curve which you have into a straight line. So now we plot the history and you have a straight line, Q versus time. Well, if you have a straight line, all you need to do is take a ruler and extend it. And you say, well, the production at this rate, at this particular time will be this, right? Very clever, very, very clever idea because rulers are easy to get, right? Flexi curve, you'll have to look for one and you may not be right on that. Okay, so that is the idea of decline curve analysis. And as I say here, sometimes they say DCA to match past production history with a model. Model means that mathematical way to make the curve into a straight line. And then do the then assume that the future production continues to follow this past trend. So you see, to do decline curve analysis, as you can see, I didn't ask you for the geology. I didn't ask you for core sample, nothing. All I said that give me the Q versus T curve. And then I took a ruler and I said, okay, your production in 2030 will be 50 barrels a day. Now I can do this for the reservoir. I can do it for a single well, or I can do it for a group of wells. And all answers will be wrong. And the reason is that the reservoir mechanism is changing. So if you know that these answers are not written in stone, then you're okay. You get a number. I'm telling you that the production in 2030 will be 50 barrels a day. Maybe in actual fact, it is 80 barrels a day, or maybe it's only 30 barrels a day. Because, you know, the reservoir production mechanism changed. On the other hand, I didn't ask you any of that. All I asked you for is production data versus time. So generally speaking, you can do a decline curve analysis, and there are different kinds of decline curves to get the original gas in place, ultimate gas recovery, remaining producing life of the well, or even the individual well characteristics. So people, clever people in petroleum engineering have taken the original theory and they have extended it to get a whole lot of information. Maybe it's not 100% accurate, maybe it's not even 90% accurate, but you have some information instead of nothing. That's the idea. But then you recall that I told you there are 4 different tools, and this is one of the tools. Another answer to compare with the other answer. So the basic equation which came from ours is this. Let me show you. Here's ours. Jan Arps, very nice person. He published this paper. When did he publish it? In 44. And he got a big SP award. And that's when I briefly met him. Very fine person. You know, I said that I'm such and such from Penn State. So he smiled at me and that was it. But now I can tell you that I met him, right? So Arps was a very clever person. He came up with a whole lot of equations. You can see them in your paper. What I'll show you are the basic equations on this slide, which is easier to see maybe. The conventional analysis, as we call it, will give you, you need the initial production, you need curvature, and the rate of decline. Those things sound like complicated, but they come right out of that simple line that are plotted. And the equation that you can use to describe all that is the production rate at any time t and the initial production rate. Those two, this one we have for sure. But the other numbers, the main number is really B and BI. Imagine that this is only one constant. Well, you know, they're related, but not to worry about it. But that equation can be fitted to that line, and you'll have all those constants. And I'll skip this one. The decline curve, this is the main thing to really know, that the decline curve can take 3 different forms, like this or like this, depending on the coordinates and the equations. Exponential decline is the simplest of them. And then there's harmonic decline and hyperbolic decline. Those things are essentially all explained by standard equations. So I'll show you one of them. So what you do, you plot production versus time, or you plot production versus cumulative production. So you see, we have now a second kind of plot. The one I said before is Q versus T. The second one says plot Q versus the cumulative production. Cumulative production is simply the integral of Q dt, which is readily available up to that particular point here. And after that, you can fit the equations. So here is the first decline. This is the most useful equation. Okay, so I skipped that unnecessary filler stuff to show you the more useful stuff. Qt, the production rate at time t, is equal to the initial production rate e to the power of minus dit. Di is simply a decline rate. So you can see that if you plot that particular data on semi-log paper, let's say if you plot Q versus log of T, you'll get a straight line. That's where the clever work of Mr. Ars or Dr. Ars comes. That he changed that equation into a straight line. Oh, it may not be a straight line. Then you have to look at his other equation. But that is the key equation. And then that equation can be used to also, just a little manipulation of that equation will give the second equation, which is Qt equal to minus di, same di, and Gp, which is the cumulative production, and the Qi there. So that's a second very useful form of the equation where you're plotting Q versus the capital Q, the cumulative production. Okay, now we come to the other two declines. We don't have a whole lot of time to devote to those, but that's the harmonic decline. And this time, harmonic decline equation is a little different. Do you see this? No e to the power of minus dit. Rather, we have qi as before, still there, but 1 plus dit. This is the harmonic decline. So it's quite possible that, let's say, the exponential decline doesn't give you a straight line. Then you say, okay, let's try this one. And lo and behold, you have a straight line and you've got it made. You have DI, and now you can do all your prediction and charge a fat consulting fee. I mean, maybe it's your own reservoir, but that's how. Okay. Now the third one is hyperbolic decline. And I've given those other equations too for comparison. Just look at the top. This is the first one, exponential. If it doesn't work, try harmonic. If it doesn't work, try the hyperbolic, which is this one. Hyperbolic is a little bit less likely, but you do run into that too. In my own personal experience, most of the time I had just exponential, but I can remember a few times when I had to use the harmonic. Never ran into hyperbolic. So here are a couple of very useful graphs. This is rate Q, which I've been showing all the time, and this is time T. And again, this is rate Q, and this time, what is this, time T again? Okay. No, everything is okay, not to worry. In one case, we are taking the log of Q. That's why you have the exponential. And in the other case, it's a straight plot. Okay. After that, you go to a different plot. At this time, we are plotting Q versus the cumulative production, in both cases. And this is a log. And this time, you can see that harmonic is giving you a straight line. So, this is very Mickey Mouse stuff. If you have the production data versus time, well, you can do all this in one afternoon or maybe quicker. Plot the data, see what it looks like. Try exponential first. If it doesn't work, try harmonic. And if that doesn't work, then try hyperbolic. Decline curve analysis is strictly, originally Mr. Ars designed it for oil reservoirs. But you can extend it to gas and it's not too bad. I've used it quite a lot. And here is an example, solved example, where we can plot the data. Here we are plotting Q versus GP, a little different example. And our equation, you saw this equation a little while ago, Q versus DIG. Here's an example. Determine the economic limit of a well. So here we have given the data. We're saying natural gas price is this, severance tax, ad valorem tax, royalty. I mean, those things are out of your pocket. And then you have also operating expense. So at what point, at what price of gas you'll have to stop? It's a very simple calculation. You can see what I've done is very, very simple. I've taken the monthly expense, 2,800 per month, and divided by the gas price. And I got, this is the economic limit allowing for all the expenses. Very simple calculation. And again, you can do it very simply by using the decline curve analysis. Here are some of the key references. Ikoku was a good friend of mine. He was at Penn State for a while. He has written 2 books, okay? One is called Gas Reservoir Engineering, and the other one is called Gas Production Engineering, okay? They're different books, useful, very useful books. Lee and Wartenberger's book, I often use that one also in my courses. It's a little hard to read, okay? But just full of all kinds of constants which you wonder where they came from. When I write all these funny constants, I spell them out so that people see where they came from. Okay, so that is our reserves. Now, a little bit about other stuff related to reserves. How about the shale gas only? Now, I'm not talking about oil. Shale gas, look at this. In the US, we have shale gas everywhere. I think I told you that maybe I didn't. The Eagleford Reservoir, which I call the biggest reservoir in the world, Eagleford, EF, was discovered in 1952. Okay. And then nobody could do anything with it. It was first produced in 2005. Production. And today, the total production right now is of the order of 4 million barrels a day. That's how America is. I don't misunderstand me. Okay, I'm not doing. I hope I don't offend you. But in America, if you do these kind of things, as I told you, it all belongs to you. So people looked at it and they said, "What's the matter with this reservoir?" They found that it was very tight. So here comes Dr. Suleiman, our department head. He is the master of fracking, refracking, and plasma fracking. Okay. Have you heard this word? This is an American word. The proper word is fracturing, okay? But we say fracking. A lot of people know that, of course. Fracking means that you hit the reservoir with a very high pressure water and sand. It's a gigantic job, doing one fracking job. And you create, first you drill a horizontal well, and then you create maybe 50, 60, maybe 100 horizontal fracks, or really they will be vertical fracks perpendicular to the horizontal. So this is the horizontal well, and the fracks are going perpendicular. And when they did that, suddenly you have huge amount of oil production, but it's expensive. So you have to draw a line somewhere. So Dr. Suleiman has been working on fracking since 1970s, but he worked with Halliburton for 32 years, and he developed all these technologies. So I call him the master of fracking. And that revolutionized the whole world, literally, because in the US, we are producing more oil than any country in the world, 14.5 million barrels a day. It went down a little bit during 2020, but it's come back now. And you see how much shale gas we have. And now if I were to draw the oil also, shale oil like this everywhere, that will blow your mind. We have so much oil in this country. So isn't that impressive that for 53 years, we knew the reservoirs, they are 400 miles long or something like that, but we didn't know how to produce it until these smart people came up with the way to frack the reservoir gigantically or massively. The word they use is massive, MASSIV, massive hydraulic fracturing. Okay, just take a word about shale gas reserves. How do you calculate those? Here's the formula for that. This formula is based upon experience. So what you see in this graph, I've plotted gas content in SCF per ton versus the density. And the units are, it's a very simple formula, empirical formula. So the gas reserves are the conversion factor, A in acres, H in thickness of the shale in feet, rho is the density of the shale. You have to know the density of the shale, okay? And CGI is what you read from this graph. And all those points that you see are actual field data. So you can calculate reserves rather quickly from this. Now, if you want to do it mathematically with all the geology, everything, then it's a very difficult task. Actually, our PhD students do that for a project. Well, we have already solved that problem, okay? We have now a new project based upon that. As I said, Dr. Suleiman is working with plasma. A plasma will shatter the rock to bits and pieces. Imagine that. This shale, I told you that, it has pore spaces 1/100th of a human hair. Very, very tight and no permeability. And think about it that we frack it, then we refrack it. How do we do it? That's a long story. And then we hit it with a plasma. Now that is still experimental, okay? And we break it to bits and pieces. So you see, currently the shale gas recovery factor, what is the recovery factor? 5% oil and gas. We have now increased to about 8% by refracking. And my own opinion is that we'll increase to 30% by plasma and other techniques. We have several techniques under investigation. One thing I didn't tell you is, what is the difference between ordinary natural gas and shale gas? None. Same thing, okay? Same thing, except that it comes from shale. Shale gas composition is very similar to the natural gas. But as I told you before, that the shale gas reservoirs may have liquid, may have even heavy oils here and there. Eagle Ford is particularly important for gas and oil especially. So if you want to look at the gas reserves, Russia has the biggest gas reserves. Iran, number 2, Qatar, number 3 or maybe number 2, hard to say. Turkmenistan, has anyone heard about Turkmenistan? This is a former Russian republic, and they have a very large gas reservoir. And the USA has 450. This is the old number, okay? We have much more than that now. Saudi Arabia, Venezuela, and Canada. Canada too has a lot of shale gas they're producing now. Just to give you an idea, USA, I think I have a slide to tell you that we have enough gas for 300 years. So trust me, oil and gas are here to stay in the world for at least 1,000 years, oil, gas, and fossil fuels in general. I mean, you may not trust me, but I know we have enough fossil fuels, including the gas hydrates, which we didn't talk about. Sometime I gave a long lecture on just that. We have enough fuel for, at the current consumption rate, for more than 1,000 years. All the renewables are okay, but they have to be subsidized, as you know. World energy used by different sources. We are using uh, currently oil equivalent of 260 million barrels a day. Our production of oil is about 100 million barrels a day. But if you take all the other fuels, our total consumption in oil equivalent kilotons of oil is that will be 260 million barrels a day. So the blue color here is coal, and the dark beige color is oil, and then gas is this dark color, and all the others are other things. Coal is here to stay. I can assure you. Okay, we have enough coal in the U.S. for thousands of years. Okay, not just a couple of years. Where I come from in India, coal, wood, cow dung cakes, those are the fuels. I use them. And back when I was living there, they still use them. They are not going to go to photovoltaics in a hurry, okay? So these fuels are going to be there for a long, long, long time. Share of energy consumption, you already saw that the top curve is oil. Oil has the biggest share. Second one is coal again. And the third one is natural gas. That's how it is. I know you said renewables are gaining ground, maybe 3%. At this point, total contribution of renewables, solar, wind, and biomass is maybe 3%. Here's a set of useful constants for you. Maybe you know some of them, but maybe you don't know some of others. Like 1 ton of oil is equivalent to here, you see here, 1 ton of oil, 1 barrel of oil is equal to 6 MCF of gas. So gas is way low priced compared to oil if you look at the energy. And 1 ton of coal is equal to 4 billions, 4 barrels of oil. You know, we can convert coal into oil. They are still doing it in South Africa, and the Germans fought 2 world wars. Would you believe? Making oil from coal. Long story there. Natural gas reserves. Gas is everywhere. Here, look at Russia. Russia is a huge country. I have a great admiration and love for Russia. And Russia, you know, it extends from here to here. 11 time zones. Can you believe that? 11 time zones. Thus, gas is everywhere. Actually, one of the biggest shale deposits, shale gas and oil deposits in Australia. US gas reserves increasing and increasing. And as I told you, we have enough for 300 years at least. Gas production, if you're interested, annual gas production for a couple of countries. Look at this. US produces 33 trillion cubic feet. Okay, this is in MMCF, and there are always 6 zeros here. Russia is number 2. Russia exports a lot of gas to Europe and other places. Iran produces a lot of gas. Iran has a lot of gas, but nowhere to sell it. They've been talking about building a pipeline all the way to India. I can assure it will be never built. There are so many countries in the way, and it's so expensive. But they talk about it all the time for the last 30 years. And other countries. China is the big player now. You see, China has a lot of shale gas too. But you know, the way we develop shale gas and shale oil, nobody can do it. It takes gigantic investment. And in the US, they do it because it belongs to you. Now, here, the last, we are at the end. Flaring of the natural gas. You know, I told you in the beginning that we are flaring 14.5 billion cubic feet a day. And you know, many times there's no choice. You have to produce oil. If you produce oil, you produce gas. And what do you do with the gas? Nothing. Most likely flare it. Try to utilize it, okay? Don't misunderstand. but a lot is flared, as you can see from this graph. Number one is Russia, number two is Iraq, number three is Iran, and number four is US. So we flare a lot of gas, something like 2 or 3 billion cubic feet a day. So this is the end. Last slide. Future of natural gas. Very bright. I wrote bright, but I would say it's very bright. It's the least polluting fuel. Least even the people who talk about renewable energy, they will agree that with that. It's a valuable source of NGLs, propane and butane. I mean, theoretically, you can take oil and crack it and make that, but that would be fantastically expensive. Propane and butane are extremely cheap because they come from gas, which is only 1/4 the price of oil if you look at the BTUs. It is also a source of what they call blue hydrogen. Do you know blue hydrogen? There's green hydrogen, which comes from solar energy. There's blue hydrogen, which comes from natural gas by steam reforming. And then there's gray hydrogen, which comes from coal. They talk about hydrogen economy and things like that. Where will the hydrogen come from? Trust me, it comes from natural gas. Once I did a study on that for a company, and I found 18 ways of making hydrogen. The only one which made sense was blue from natural gas. US, I told you, has enough hydrogen. Oh, I wrote the wrong word here. Sorry about that. Natural gas, sorry about that. It has enough natural gas for 300 years or more. And then finally, natural gas is cheaper than electricity. Would you believe that? LNG is more expensive. Well, LNG is that you take gas and you liquefy it and then re-evaporate it. And typically LNG, like in Japan, the gas price in Japan is of the order of $15 per MCF, SCF or MCF. Whereas in the US, you just saw we are paying about $2.50 for the same. And it's understandable. And you know, $15 per MCF is not inconceivable. About 15, 20 years ago, gas became scarce in California, and we were paying $12 per MCF. Okay. Okay, well, this is all we have. I hope I covered some of the basics, and I hope you enjoyed this stuff. Thank you very much.
Thank you, Dr. Farouq Ali, for this enlightening session. Now we'll move to answering some questions asked by our honorable audience.
Okay.
Someone says in Bolivia in 2018, he drilled a well of 26,200 feet, and it was a dry well. If it had been a positive well, what considerations should we have to calculate for the natural gas resource for an ultra-deep well of this type?
Oh, those are very rare and special wells. The deepest well ever drilled was drilled in Russia called the Kola well. Kola is a peninsula in northern Russia. That was about 45,000 feet, twice as deep as you're talking about. And the one after that, the next one, which was the deepest well, was in Germany, which was the KTB well, which was about 36,000 feet. Kola was about 45,000 feet. And this one that you talk about. Now, in the US, we have drilled wells of that order. I don't remember any particular well. The main thing about those wells is that we learn a lot about what kind of rocks there are and where will be the next place to drill where we may find gas or we may find oil. So we should take, that is a very valuable well. If we have all the data from there, we can get a whole lot of information from there. Now, Bolivia, I've never been to Bolivia. I've been to 4 countries in I've done a lot of work in Brazil, Colombia, Venezuela, and Argentina, and I was going to go to Bolivia, but I found that that it may not be very safe because it's quite high altitude, and so in the end I didn't go. But Bolivia has a lot of gas, and they may have shale gas also. I talked to somebody who did a lot of work on gas in Bolivia. Any other question?
Okay. Yes, moving on to the next question. Someone says, how do we know which decline curve analysis method has to be used, or which one is going to be the best fit for the reservoir?
Well, the answer is none. But no, that's not completely the full answer. The answer is this, that take your data. You can take the data for the whole field. You can take the data for a portion of the field. You can even take the data for a well, up to you. And then you plot the Q versus T and see what does it look like. And then see whether it will go, you could replot it as an exponential. If you're lucky, maybe yes, and then it's a straight line, and now you can make a prediction. As I said before, that notice that you're doing all that without any data. All you have is the production rate versus time. So it's amazing. It's rather amazing how much you can do with those decline curves. That's why people still use them. They will do simulation only if they feel that decline curve is no good, or maybe the volumetric is no good, then they will go to simulation. When you do simulation, you're looking at maybe 6 months work, maybe 1 year's work. Decline curve you can do in 15 minutes. So you use your judgment. After you plot the first curve for whatever area you choose, then you use your judgment as to which of the 3 will be best. Try them all.
Okay, thank you, Doctor. Moving on to the next question. Someone says, are methods of calculations of gas reserves mentioned in your presentation applicable for unconventional gas reservoirs like shale gas, for example?
Well, you can do that, but there's a paper. I don't have it on my hands right now, by Bike and Akatulu. This is a SP paper. And here they talk about a BG factor for a gas reservoir, where the pore space is of the order of nanometers. In the pore space in the reservoirs is in nano. Nano means 10 to the minus 9 nanometer size or something like that. As I said, that they're very, very small pores. So you may try that approach for shale gas reservoir by using Bayek and Cthulhu's BG. Maybe it might work. But keep in mind also that if the pore size is of the order of the molecular size, then the calculations won't be valid, because then the molecules are interacting with the walls of the pores, and the answer won't be very accurate. But the other thing is this, that this kind of reservoir will always be fractured. So once you fracture it, then you're dealing with a totally different ball game, as they say, because the fracs will have very high permeability, high productivity, and you can get close to essentially a conventional analysis.
Our next question is, which average pressure calculation method is more accurate out of the 3 shown in the presentation?
Well, it's like this. If you to take the simplest situation, where you have a reservoir, and let's say there are several wells here, 3 wells here, and you want to know the average pressure. Then, given that reservoirs and the measured pressure in the 3 wells, you can then say, okay, we can divide the reservoir into 3 portions like this, based upon your experience, and weight the pressure values on those volumes. That's one way. If you have a lot of pressure data, then of course the best way is to do iso pressure contours, like I showed you, and then find the average pressure. And then keep one thing in mind, that we may have well test data too. You see, depending on your field, you may be doing a well test here now and then. A well test will give you the average pressure over the radius of investigation. You know that? So if you know the radius of investigation, now you have an average pressure over that area, and you can compare it with those 3. So it's like this, that again, there are so many uncertainties that you have to use all those 3 techniques to see which one gives you a value which makes sense, or maybe you need to get an average, something like that. I've had this situation quite often, and I put a great emphasis on the well test data. Any more questions?
Well, that's about it for the questions today. It was a pleasure
Okay.
having you on Petro, Dr. Farouq Ali. Thanks for joining us, and thank you everyone for tuning in with us today. Today's session will be uploaded on Petro YouTube channel. You might want to check that out for your quiz. Thanks again. Have a great day.
Thank you for attending. I appreciate that. I wish I could see you all. Bye. Bye, Joanna.
Thank you, Dr. Farouq. Have a great day.
You too have a nice day.